Welcome back, guys. Sorry about the delay. Had a little bit of a technical problem. Okay, well, uh, here we go. We're at about 45th day. I got to do and certify my number of students that I have. So we're at 45-day mark, and midterms coming up here in a couple of weeks. So maybe take a little break. All right. Well, let's take a look at first our calendar. Again, I always look at this periodically because I want to make sure everybody understands where we're at. You can see now the assignments are pretty much spreading out compared to where we were, early. We were kind of filled up with assignments, so they kind of spread out. We are going to be doing chapter 8 today, which deals with what is called nomenclature, which is the fancy word for name that compound. And I have been doing that as we progress little by little, but we're going to get more into detail with respect to how to name the compound. So what can happen is one or two things. One, you could be given the formula, which we began to write formulas, okay? And then from the formula, give the name, or vice versa. Given the formula, work backwards and given a name, let me try that again. I haven't had enough coffee yet. Given the name, give the formula. Given the formula, give the name. Okay, there, I got it right. Okay, that's eventually what the whole purpose of this chapter is about. Now, let me refer you quickly to the periodic table. And I mentioned this before, but I'm going to go over it again. I have highlighted 16 elements that, when they become ions, will have a specific charge / oxidation number, okay? We know that everyone in group 1, excluding hydrogen, okay, because hydrogen, we're talking about metals here. Hydrogen is not a metal. Everyone in group 1 has 1 valence electron. Therefore, when they become ionic, become a cation, they all have a +1 charge. Everybody in group 2 has 2 valence electrons. Therefore, they will lose 2 valence electrons, being metals, fulfilling the octet. Okay, fulfilling the octet, because that's the driving force here to get to that octet, 8 electrons around it. But every ion there will have a +2 charge. Okay, I didn't say every element there. I said every ion, because remember, the elements become the ions by losing or gaining electrons. In this case, everybody is losing electrons because they're metal. So that gives us 12 ions that you know, or should know, or will know 100% of the time what their oxidation number is. Okay, there's 12. 6 of them from group 1, 6 of them from group 2. Now, excuse me, the other four that have a constant oxidation number, I've highlighted them, and they're starting with aluminum. Okay, and one way to remember them, I've found that if I were to go, starting with aluminum, number 13, and go across at an angle, and then go across to the right. So at an angle, bottom left, from aluminum, we go across diagonally to zinc, we go then to silver, and then from silver, we shoot back to cadmium. Aluminum has a +3 charge 100% of the time, okay? Zinc has a +2 charge 100% of the time. Silver, Ag, when it becomes ionic, always has a +1 charge. And cadmium, Cd, always has a +2. And so there we have it. We got 16 ions that 100% of the time what their oxidation number is. There's only 16, okay? That means that all the rest of the metals there, okay, have a variable oxidation number, and they can vary from +1 to a +9. Okay, depends on the reaction condition. So we cannot unequivocally determine that, yes, copper will always have a +2. We can't say that because copper, Cu, can exist either as a +2 state or a +1 state, depending on how many electrons are lost. So copper 1 and copper 2 have very distinct properties. They're different compounds. One is a blue color in solution, very nice, pretty blue color, and the other one's a green. Okay, even the colors are different. Iron's the same way. Iron can exist either as a +2 or a +3. Right, so we don't we don't know the oxidation numbers of those, and so we have to name them, give them a specific name, and we use Roman numerals, and we'll get more into that in a second. We use Roman numerals to determine, well, which one are we talking about? It's kind of ambiguous, right? Because we got copper 2, copper 1, which one? How do we distinguish them? Well, we do. We use Roman numerals, and we'll talk about that. Now, with respect to anions, okay? With respect to anions, let me get this here. And let's see, we'll do it in red color. So when we look at nitrogen and phosphorus, okay, those are the main ions, anions that we're going to be working with. Same is true with oxygen and sulfur. And then the doesn't mean that the other ones we don't work with, but those are the main ones you're going to see a lot of with respect to anions. And we see the fluorine all the way down to the iodine. Okay, those are the elements. Now, nitrogen and phosphorus end up with a -3 charge. We know that because it's a nonmetal. It's in group 5. It's going to want to pick up 3 electrons. So we end up with a -3 charge for group 5, the nitrogen and the phosphorus. The nitrogen, its name becomes nitride, Nitride, nitride. The phosphorus, its name now becomes phosphide, okay? And so that's how we distinguish them between being the element and the anion. Oxygen and sulfur, they're in group 6. They're going to pick up 2 electrons, have an ionic charge -2. Oxygen, its name goes from oxygen to oxide. The name sulfur goes to sulfide, okay? And then the group 7 elements, the halogens, the fluorine, the chlorine, the bromine, the iodine, when they become ionic, they pick up 1 electron because they're in group 7. Okay, they are nonmetals and therefore prefer to gain electrons because by gaining 1 electron, now they have the octet full. All right, and they become isoelectronic with the noble gas in front of it, which again, I said becomes isoelectronic. It does not become the noble gas. A couple of questions were answered in that manner. They become isoelectronic. They share the same number of electrons. All right, so fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, and iodine becomes iodide. Okay, and so with respect to the anions, there is a name change. With respect to the cations, there's no name change. Sodium remains sodium. How we distinguish them, we will say sodium atom or the element sodium versus the sodium ion. That's how we distinguish the two between the element and the ion. The anion, how we distinguish between the element and the ion is a complete name change. And we end up removing the last letters of the name and adding IDE, IDE. Okay. All right. So If you haven't done so, you may, mark up your periodic table with that information, okay? Because we're gonna be using this quite a bit. All right, so this brings us to chapter 8, aka nomenclature, okay? Or basically name that compound. So names of atoms, simple neutral atoms, the name, like I just stated, stays the same. We got sodium is sodium atom. We're talking about the element, and neon is the neon element. Now, we talked about this also earlier. Know the names and the symbols for at least the first 20 elements. Then add these onto the list. We got Ba, which is barium, Co, which is cobalt, I, which is iodine, Cu, which is copper, Fe, which is iron, Pb is lead, Hg is mercury, Ag is silver, Au is gold, Zn is zinc, Sn is stannous, or you can use the word tin, Tin. Okay. This morning when you brush your teeth, you probably, if you look at the label, you probably brush your teeth with stannous fluoride. You never knew, right, that you were brushing your teeth with tin, Tin, but the ionic tin. Okay, strontium Sr, Ni for nickel, Br for bromine, Cr for chrome, Mn for manganese, Cd for cadmium. Okay, so be familiar with this, and we're going to be adding more as we go along. Okay, refresh your memory with respect to ionic compounds. Ionic compounds is a combination of a metal and a nonmetal. Okay, covalent compounds and nonmetals only. This issue here sometimes gets confusing, but if you it's important that you distinguish the two. Why is it important? For multiple reasons, but with respect to ionic compounds, you would notice that so far when we were talking about covalent compounds, like we mentioned carbon dioxide, okay, and its name CO2, carbon dioxide. Notice there's a prefix, di, meaning two oxygens, carbon dioxide. But if you got and that's a covalent compound. Now, if we did the same thing with, say, barium chloride, BaCl2, we would just name it barium chloride. We would not use the prefix barium dichloride, okay? And so ionic compounds do not use prefixes to count the number of atoms used, whereas covalent compounds, with respect to their names, yes, they use prefixes. Carbon dioxide, carbon monoxide, one oxygen, okay? And don't mix and match. No prefixes for ionic compounds, yes for covalent, okay? Now we had the monatomic ions that we have talked at length about. We got the sodium ion, chloride ion, calcium ion, so on and so forth, with their respective charge. We also have the polyatomic ions. This is listed on the periodic table to refresh your memory. On the periodic table, left-hand corner, bottom left-hand corner, we have the most common, there's thousands of these, but the most common polyatomic ions are listed here. Okay, we only have one cation, and the rest are anions, all negative charge. Again, those are units. We don't separate them. We keep them together. If we need more than one, we use a parentheses and then the subscript outside the parentheses to designate that we need two of these polyatomic ions, or three or four, or whatever number we need. If we need just one, we just don't need a parentheses. Only if we need more than one. And they have their own specific name. For example, NO3 negative. Okay, that is called the nitrate ion, polyatomic ion. And then right below it, we have NO2 negative. Both have the same charge, but it has a different name called nitrite because it has one less oxygen than the nitrate. Okay. Notice something interesting here, so you won't confuse you, is if we were dealing simply with the atom itself, the nitride, remember it's nitrogen, becomes ionic, it would be a -3, and its name would be as follows. Okay, the N-3, the single element nitrogen, is called nitride. When we put a nitrate, Nitrate, the 8 should tell you I'm dealing with oxygen, nitrogen bonded to oxygen. Okay, and in this case, it has 3 of them. Notice a similar aspect when it comes to sulfate, which is the SO4. Okay, that is sulfate. Now, this polyatomic ion has a -2 charge. The whole thing has a -2 charge. Take off 1 oxygen, then you have the sulfite. And it's analogous to the nitrate and the nitrite. Okay, not to be confused with sulfide, which is the single element. And let me see if I can put it right there. The -2. Oh. Okay. Notice how the naming works. When we talk about sulfide, it's simply the atom single by itself and with a -2 charge. -2 because it's in group 6, it's going to become ionic, take up 2 electrons. Okay. So they have their own name now. Oxidation state. I've been using the term charge. Okay. And you'll see me, excuse me, I will convert little by little to the term oxidation state, which is just simply the charge, either negative or positive. Okay. All the elements have a 0 charge. Now, why is that? Because they all have equal number of protons, equal number of electrons. So we end up with a net charge of 0. Okay. Equal positives, equal negatives. Now, elements, they have a charge simply because, as we know now, hopefully, that we either lost electrons or regain electrons. Okay. And therefore, their oxidation state has changed. Now, I already mentioned to you this, I call it the 16, the sweet 16. Okay. Those 16 elements have a fixed charge. You know their charge 100% of the time. Here, silver and zinc are listed, and we also have aluminum, which is +3, and cadmium with a +2, and then plus group 1 and group 2. Those are fixed charge elements. Okay. Everything, all the other metals, okay, all the other metals have a variable charge. And there could be several possibilities. It can go all the way from a +1 to a +9. I list here a couple of possible examples: copper 1, and copper 2. Okay. Now, cations, we know this. They're just simply metals that lost electrons to become cations. We also talked at length about the respective charge, group 1, group 2, 3. Okay, and their respective charge or oxidation state, the new oxidation state as they become cations. Okay, because all the other metals can vary from a +1 to +9. I gave you the 16 to have a constant oxidation number. Now, how do we distinguish the others? We use Roman numerals. Okay, for example, copper, as we listed here, we write out copper and then parentheses Roman numeral 2. What that tells you is that is the oxidation state of copper. In this case, it's copper +2. Okay. Iron 3 plus 3, when we write that out, we write iron parentheses Roman numeral 3. Lead in this state has a plus 4. Therefore, we write lead parentheses IV, okay, to represent the oxidation state of that variable oxidation state metal. So if it was copper 1, then we would use Roman numeral 1, okay? And we do this for the other, all the other metals, excluding the sweet 16. The 16 doesn't use Roman numerals. Why? Because they're constant oxidation state. They're always going to have that oxidation state. Therefore, it's not necessary to write the Roman numeral. So sodium chloride, NaCl, would simply be sodium chloride. It would not be sodium Roman numeral 1 chloride. It would be sodium chloride. Okay. Okay. We talk about nonmetals. They're going to gain electrons. Group 5 with a -3, group 6, -2, group 7, -1. And we all know, hopefully by now, that group 8 will always have a oxidation state of 0 because the octet is full for all the noble gases. They're very unreactive. It's a duet, the duet for hydrogen, helium, excuse me. Okay. All right, all got valence electrons. Now, we're going to be talking about the metal and non-metal combinations. We're going to start learning the formulas and names for ionic compounds. Now, as we progress, keep in mind, you can do a ton of mix and match. Okay, we may be doing examples of certain cations and certain anions, but remember, I can intermix these things. Okay, so you probably have access to, I don't know, a couple thousand compound names, if not more. Okay, and remember that ionic compounds, when we're talking about metal, non-metal, are ions. Now, the sum of the charges must equal 0. Okay, let me rewrite this to a general formula for you. So you might want to put this in your notes. Okay, the number of cations plus the number of anions, okay, must equal the charge of the molecule. This general formula would encompass all the possibilities you have, okay? Most of the time, the charge of the molecule will always be 0. However, if you look at the polyatomic ions, like the sulfate, SO4 -2, in that case, the charge of the molecule is a -2, okay? And you can use this formula to determine, you can do 2 things. One, using this formula, keeping this in mind, tells you how many cations and anions I need to put together so they equal 0, okay? Using that, it's the same thing. The sum of all charges must equal 0. I can also use it in case I don't know the charge of the cation, for example, but I do know the charge of the anion, and I know the charge of a molecule. So I can use it to calculate the charge of the cation. It's a simple algebraic equation, A plus B equals C. I either know A, I know A and B to give me C, or I may know B and C to give me A, or I may know A and C to give me B, any combination thereof, okay? And this is what it is, because you'll find in the homework problem, there are some examples where the charge of the molecule does not equal 0, has a specific charge, okay? All right. Now, in our examples we do here in the lecture, we're always going to end up with whole numbers. But it is possible with respect to the homework to get numbers that are, less decimal numbers or fractions. But here we're always going to end up with nice, even whole numbers. Okay, with that being said, let's continue with the polyatomic ions. Here it is. Okay, we talked at length about these, so you should become very familiar, at least know where they're at on the periodic table so you can use it. And the other aspect of bottom is we keep them together. Okay, they are a group, they are a packet. And if we need more than one, we're gonna put parentheses around them with the subscript. Okay, we'll run into some examples here in a bit. When we put them together, the cations and the anions, they must be neutral. So we end up with 0. So adding enough cations and enough anions equals 0. For example, combine sodium and nitrogen. Well, the first thing we need to do before we can combine anything is we need to convert the element into the oxidation state. Okay, sodium we know is in group 1. It's a metal. It's going to lose 1 electron, so its charge is a +1. Nitrogen is in group 5. It's a nonmetal. It's going to pick up 3 electrons. Therefore, it has a -3 charge. Okay. And so now I'm going to put the sodium and the sodium ion and the nitrite ion together, but I have to put them together such that they equal 0. So you can see that I need 3 positives to cancel the -3 of the nitrite, excuse me. So that 3 becomes the subscript. So the formula would be Na3N. Okay, sodium. Throw in the name here. Sodium nitrite. Now we use sodium here, but guess what? We could use any of the group 1 metals. We could have used potassium. We could have used lithium. Any one of them, cesium. Okay. And already we just with the group 1 metals, we can easily make 6 new compounds there. Okay, you just change the name of the metal. Okay, so here they're asking you, okay, what is the formula? You're given the elements. So step 1, when you're given the elements, step 1, before you do anything, get into a little routine so you can have a systematic approach to these problems. Okay. Step 1, take the elements, convert them to ions, their respective ions. Okay. Sodium, like we talked about in number 1, we all know, hope by now, that it is a +1 charge. Okay. Sulfur, okay, go find it in the periodic table. It is in group 6. So when it becomes ionic, it is a -2. And its name changes to sulfide. Okay. So those are the ions that I'm going to be working with. I got a +1 from the sodium, -2 from the sulfide. Okay, that tells me I need 2 sodium cations, right? So that 2 now becomes the sulfate or the subscript for the number of sodiums. And the name becomes sodium sulfide. Okay, so there's a formula, Na2S. Okay. All right, the next combination. You have let me organize this a little better. Okay. All right, similar scenario. We got to get the magnesium. We know it's in group 2, so it's going to have a +2 charge. Okay. We know the oxygen is in group 6. So it will end up with a -2 charge. And the name will be magnesium oxide. Notice there's no prefixes here, okay? No prefixes, it's just, well, we need one. So we got magnesium with a +2 charge, oxidation state of a +2. We got the oxide with oxidation state of a -2. So it's straightforward, put them 1 to 1. And the formula becomes MgO. The name is magnesium oxide. Now I'm writing the name down because, again, look at the name and work back to the formula and vice versa, okay? So you can be given the name, ask for the formula, or you could be given the formula, ask for the name. Okay, next one. Potassium and phosphorus. Okay, so same thing. Potassium is in group 1. But we know that it will have a +1 charge, okay? Phosphorus is in group 5. Group 5 tells us that it will pick up, guess what? 3 electrons, right? And its name is potassium. The name of the metal stays the same, but it went from phosphorus to phosphide. That's the name of the anion. Now, you can see phosphorus has a -3. Potassium has a +1. So I need 3 potassiums to counter the -3 of the phosphide. So that 3 becomes the subscript for potassium. And our formula becomes K2P, potassium phosphide. All right, here's going to be somewhat of a challenging one, but give us some thought here. Okay, first step, as usual, let's break down the ions. We have calcium. Calcium's in group 2, excuse me. And so it will have a +2 charge. Okay. Nitrogen is in group 5. So it will have a -3 charge. Okay. So now you have a little bit of a challenge, right? A little bit, but let's get the name. We got calcium. Then nitrogen becomes nitride. Okay. All right. That's the name. We got the name, but we got the ions, but we got to put them together such that they equal 0. However, we got a +2 from calcium and a -3 from the nitrogen. Any suggestions? Because we can't put them together 1 to 1. Because if I put them 1 to 1, I'm going to have an excess of a -1, right? Because the +2 is only going to cancel -2 of the nitride. That leaves me with a -1. So that won't work. I want to put them together with enough of each so they cancel each other out. So what could you do here? Maybe think about what would you do if you needed to add the fraction 1/5 plus 1/7. What do we normally do when we add fractions? That are not the same denominator. We look for a common number, do we not? Those common denominator. Okay. Well, think of it here. I got a +2 and a -3. What number would each one have in common? Or what can we do to get them into equal charges? Well, let me ask you this. What if I were to have 3 calciums and 2 nitrates? What would be my overall positive charge if I had 3 calciums? with each one with a +2. What's my overall positive?
+6.
+6, exactly. And my nitride with 2 of them, each one with a -3, okay, has a 6. That's correct. But have a -6. So if I use 2 nitrides and 3 calciums, the overall charge is +6 and -6. They cancel each other out. So that number I put up front now becomes the subscript for the formula. You see that? 3 calciums at a +2 gives me overall +6. 2 nitrogens with -3 for each nitride gives me overall -6. I got sufficient of each one, numbers of each one. The name is simply calcium nitride. Notice it is not tricalcium dinitride, okay, because this is ionic. These are ionic compounds. Ionic compounds don't use prefixes, okay? Now, way back when they used to, but they don't do it. You know, we don't do that. There's a question there. I don't understand the symbol, the greater than divide symbol. No, Severine, you had a question? You have you type some symbols, the greater than equal to symbol and the divide symbol.
Sorry, by accident.
Oh, okay, no problem. Because I was trying to understand what the question was. All right. Okay, so let's move on to the next one. There's a little, if you think about this for a second, I want you to think about this, right? Something to kind of help you out. All right. If you look at the subscript of nitrogen, which is a 2, isn't that the charge of the calcium, right? And if you look at the subscript for calcium, isn't that number the charge for the nitride? As it's as if the corresponding charge you can use and do a little cross there to help you out to figure out the subscript. But if you don't see that, don't do that. It will confuse you. Just stick with, I got it, three positive 2s and two negative 3s. Okay. All right. All right. Here we got aluminum. Same scenario, similar scenario. In that, first thing we do is we first put everything into ions. So aluminum, being in group 3, being a metal, will have a +3 charge. Okay. And chloride, being in group 7, will have a -1 charge. Okay. And now we're going to put them together such that they cancel out, the charges cancel out. So that means that I need 3 chlorides to cancel out the +3 of aluminum. And the name is simply aluminum chloride, not chlorine. Chlorine is the element. It's now become the ion, in this case, the anion. Okay. So the name is aluminum chloride, AlCl3. Now, as we're going, let's think about, you can start mixing and matching. The first one, sodium. Well, I can use sodium with oxide, sodium with phosphide, sodium with nitride, sodium with chloride. Magnesium, I can mix it up with sulfide, mix it up with phosphide, mix it up with nitride, mix it up with chloride. You see? Just mix and match. I got 1, 2, 3, 4, 5. I got 5 sodium compounds. 5, 10, 15, 20, 30. At this point, you got 30 compounds that you can make. just with these 5 that we put together by interchanging, mixing up the cation and the anions, because I can mix the aluminum up with the sulfide, the aluminum up with the oxide, aluminum with the phosphide, aluminum with the nitride. See how that goes? And we got chloride there, but bear in mind, you can do all that with all the halogens, the fluoride, the chloride, the iodide, okay? And the bromide, excuse me, that one too. So your number just keeps adding up as far as the different combinations that you can do. All right, don't forget the study mate that I have on the Canvas course. The study mate is specifically nomenclature. There's 143 combinations of formula and name that will help you out with respect to this chapter in naming compounds. Okay. Now, why is that crucial? Because once we get the names out of the way, you could be given a sentence or two to describe a chemical reaction. And from that sentence, you're going to convert that sentence into a chemical reaction. And then from that chemical reaction, we're going to what we call balance it. We'll put it the equal number of elements both as a reactant and as a product. And from that balanced chemical equation, now we can do some calculations, okay, to determine, let's say, how much product of something we need, starting with X amount of reactant. It's all tied in together. Okay, so now we have zinc and we have iodine. Iodine, we see, we're starting with the elements. So first step, convert them into the ions, like we've been doing. Zinc is one of the sweet 16. Always has a +2. And iodine, well, iodine being in group 7 now becomes iodide with a -1 charge. Okay, we need 2 of the iodides. Okay, zinc iodide is the, and we could have used chloride, we could have used bromide here, we could use oxide, we could have used another combination. Any of these. So our formula is ZnI2 because we need 2 iodides to cancel out the +2 of the zinc. All right, a little bit different here now. This time they give you a variable oxidation number metal. Copper is not part of the 16. So we have to tell you which oxidation state you're working with. And they do that by using the Roman numerals. The Roman numeral there tells me that I'm using copper 2. Okay. Oxygen is in group 6. When it becomes ionic, it becomes a -2 charge. Okay. The name here is copper, Roman numeral 2, because that is the oxidation state we're using. Oxygen becomes oxide. Okay. They're both plus, there's a +2 and a -2. So I can simply do a 1-to-1 combination there to cancel each other out. So the formula is copper, the formula CuO, and the name is copper, Roman numeral 2 oxide. Remember, the Roman numeral here applies to the metal only, does not apply to the non-metal part. That tells you what is the oxidation state of that metal. Okay. There's another example. We got Pb, which is lead. Okay. And they're telling you 4, Roman numeral 4, which is lead +4. So we got Pb, oxidation state, oxygen becomes oxide, which we know just from the previous example is a -2. Okay. And since lead has a +4 and oxide has a -2, that means I need 2 oxides, right? I need 2 oxides to cancel the +4 for the oxygen from the lead. Okay. Name-wise, lead, Roman numeral 4, oxide. Okay. The formula is simply Pb and then O2, because I needed 2 oxygens or 2 oxides to cancel the +4 from the lead. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, just here you have 64. Yeah, 8, 9, yeah, 64 combinations of different compounds. I mean, I start with sodium and sulfide, but I can go sodium and oxide, sodium and phosphide, sodium and nitride, sodium and chloride, iodide, etc., oxide. So we're starting to build up our library of chemical compound namings and formulas. All right, so let me cancel this. So, right, so every time you put a metal and a non-metal together, we're talking about ionic compounds. You know, you make sure that they add up to 0 when we're putting them together, okay? Now, remember the general formula I gave you earlier where I said the total number of cations? Well, I'll come back to this. Yeah, let's talk about the polyatomic ions. Question is here, we're gonna write the formula. Well, for the polyatomic ions, obviously they're going to give you the charge. So the only charge you need to determine would be the charge of the metal in this case here. And so here we have magnesium, which is a +2 charge, right? It's in group 2, so it's got a +2 charge. And the oxide, hydroxide, has a OH has a -1 charge. Okay, that's one of the polyatomic ions. That's the hydroxide. So I need to have 2 of these. I'm putting parentheses because remember, this is a polyatomic ion. I don't separate them. I keep them together as a unit. And if I need 2 of them, that means that I need a parentheses, and that 2 becomes a subscript. And so my formula is MgOH parentheses OH2. Let me slide this over a little bit. Okay. And the name will be simply magnesium hydroxide. The hydroxide is the polyatomic ion. So you can get that name from the table on the periodic table, hydroxide. Okay. Here we're using, again, the polyatomic ion, that's PO4 -2. Well, where do I find the PO4? Well, here we go. PO4 -3, excuse me. Okay. Its name is phosphite. Okay. We just did the OH negative. That's a hydroxide ion. Now we're doing the PO4 -3. That's called the phosphate. So that's the name of it. We don't change anything. It's not phosphorus, tetraoxide, anything of that sort. Simply phosphate. Okay, let me go back. And you can see that it has a -3 charge for the whole unit. The potassium, hopefully by now you realize that that is a +1. Okay, because it's a group 1. I need 3 of them to cancel the -3. So the formula becomes K subscript 3, then PO4. Since you only need one, there's only one PO4, you don't need the parentheses. It is only when you need more than one that you use a parentheses, okay? All right, let's look at this one. SO4. Well, until you become confident with it, until then, look it up. SO4 is the sulfate polyatomic ion, right there. Not the sulfide. If it was sulfide, IDE, it would be sulfur all by itself, but this is the sulfate, okay, the SO4 negative 2. And you look at silver, silver is one of the 16, remember? One of the 16, and that had a constant oxidation number of a +1. And so silver has a +1. The sulfate has a -2. So I need 2 silvers, okay? And so I got, let me, I should write the names down for you here. But this is magnesium hydroxide, okay? Potassium phosphate and silver sulfate, okay? Notice no Roman numerals here so far, right? Because magnesium, potassium, and silver are part of the 16. Therefore, no Roman numerals are required here, okay? All right, next one. We have calcium and nitrate. Calcium, I'll leave it to you, is in group 2, has a +2 charge. The nitrate, the NO3, which you find in the polyatomic ion, has a -1 charge. That means we need 2 of them. So I need a parentheses, okay? I need a parentheses to show me that I got 2 nitrates. Its name would simply be calcium nitrate, not the nitride. Nitride is this nitrogen all by itself, just like the sulfide would be the sulfur by itself, okay? So we got calcium nitrate, excuse me, okay? Yeah, be careful. Sometimes you'll see that they put in NO2, which is the nitrite. If they use NO2 negative, then this would be calcium nitrate. If they would have put SO3 -2, that would have been the sulfite, okay? All right. Now, again, here, keep it in mind, you can mix and match here. I can do the magnesium with the phosphite, the magnesium with the sulfate, the magnesium with the nitrate, okay? The potassium with the hydroxide, the potassium with the sulfate, so on and so forth. All right, all right. Now we have the metal that is not part of the 16, and therefore it is a polyatomic ion. First of all, the first polyatomic ion is CO3 -2. You look that up in the periodic table and you find it to be called carbonate, okay? Let's go look, let's go take a look. CO3-, which is right there, CO3-. You'll find that a lot of that in baking soda, okay? Carbonate, chalk, find a lot of that in chalk through carbonate. And you're using copper 2, because again, they're giving you Cu Roman numeral 2. That's a +2 charge. So we get a +2, a -2. We can simply put them together as a 1-to-1. And unfortunately, I lost the other names. but I will continue with this name, and this would simply be copper, Roman numeral 2, carbonate. Okay. All right. So let me go back to make sure you got the names here. Magnesium hydroxide. Potassium phosphate. Silver sulfate. Calcium nitrate. Okay. The first four did not use Roman numerals because they have fixed oxidation numbers. Okay. Copper does not. Hence, you're given which oxidation number you're working with. If this were, for example, let's say that they gave you Cu Roman numeral 1. Okay. Well, that's +1 charge. So that means that I would need Cu subscript 2, okay, and then my carbonate subscript 3. Sorry, I can't make the subscript. Okay, so if I was using copper 1, and then its name would be copper 1 carbonate. If I was given the copper 1. Okay, so the thing to remember here with respect to polyatomic ions, that you use the parentheses when you need more than one polyatomic ion. You don't add subscripts. The fact, like up in here, the hydroxide, I've seen before where people would put a subscript on the oxygen, it would be O2H2. That would be incorrect. I have no idea what that is. H2O2. Or they would put, any number of subscripts in the polyatomic ion atoms. Don't do that. Again, I can overemphasize the polyatomic ions are units. They're a group. You keep them together. You need more than one. You use the parentheses and put the subscript on the parentheses. All right, so naming ionic compounds, which we've been doing as we progress, and this is all about. So we don't use for fixed charge metals. We don't use a 16. We don't use Roman numerals. Okay. We've been talking at length about the anion and the name and how they change. So chlorine becomes chloride. So the name here is sodium chloride. Okay. The name here would be, we got potassium and bromine, which is now bromide. So that's potassium bromide. We have magnesium, then we have oxygen. Okay. The fact that you see oxygen by itself and it follows a metal tells you it's in the oxidation state. Okay. And so you can automatically say, okay, it's oxide. So this is magnesium oxide. Here we have calcium. And then you might be tempted to think, oh, Fe2, the diatomic fluorine. But remember, there is a calcium preceding the fluorine, the two fluorines, okay, as you may look at it. The fact that there's a calcium in front tells you, we're not dealing with fluorine, we're dealing with fluoride, because that's an ionic compound here. The name here would be calcium fluoride. Lithium, then we got sulfur. Okay, so it'd be sulfur becomes sulfide. Lithium sulfide. Silver, and again, chlorine becomes chloride, just like bromine became bromide. Now, okay, notice here we don't use Roman numerals again because they're all the metals in these examples were part of the 16. They're not variable oxidation numbers, okay? And we didn't use any prefixes. So for example, number 3 is simply calcium fluoride, not calcium difluoride, okay? Nor is it number 4, dilithium sulfide. It's simply lithium fluoride, sulfide, okay? So no prefixes and no Roman numerals for any of the metals that are part of the 16, okay? All right, so, and again, you can mix and match. We got potassium and oxygen, calcium oxide, calcium fluoride, calcium sulfur, potassium oxide, potassium fluoride, potassium sulfide, potassium chloride, and the same with magnesium. Magnesium bromide, magnesium fluoride, magnesium sulfide, so on and so forth. So you're mixing and matching again. So you're creating a lot more compounds as we progress. Okay. For the polyatomic ions, as we talked about it, we don't change the name. Okay. A good rule of thumb, if you want to think about it, because people have a hard time recognizing sometimes that you're dealing with a polyatomic ion. Okay. Now, if you look at like NO3 nitrate, okay, if you see nitrogen and then immediately following nitrogen in the formula, you see oxygens, then we're not dealing with nitride. We are dealing either with the nitrate or the nitrite. The same is true with the sulfur. You see sulfur, but then immediately following sulfur in the formula is oxygen. That tells you you're dealing with the polyatomic ion, either the sulfate or the sulfite. Okay. And chrome is the same way. Chrome immediately followed by oxygen is the chromate, and so on and so forth. Carbon, you might want to think, oh, wait a minute, I got carbon dioxide, for example. But if you see carbon and then immediately following carbon, there are 3 oxygens. Okay, that's an indication that you're dealing with the polyatomic ion carbonate. And nitrogen followed by hydrogen, specifically 4 of them. Again, on the ammonium. All right, so let's go back to the slide. And so here we got potassium, 3 potassiums, and then we got phosphorus. And then we might think phosphide, but immediately following the phosphorus, we have 4 oxygens. That should direct you to the polyatomic ion table. Look it up, you'll find it to be phosphate. Potassium is potassium, no name change there. That polyatomic ion is phosphate. So that is potassium phosphate. Okay. Immediately when you see a parenthesis anywhere in the formula, automatically think polyatomic ions. So in the parentheses, you have the OH. You go to the table, you find the OH minus, which is the hydroxide. And so this name would be calcium hydroxide. Okay. Here's another example of the sulfur that you may want to think sulfide, but immediately following the sulfur is oxygen. So that tells you polyatomic ion, specifically 4 of them, which on the table shows it to be sulfate. And then the metal is simply zinc, so it's zinc sulfate. Okay. Now, excuse me. We talked at with variable charge metal ionics. Okay, notice the ones we just did they're not variable charge. So the metal remains whatever the name is. It is only when we have a variable charge, which is any of the metals that are not part of the 16 list I gave you, then we use Roman numerals. And the thing is, well, how do we know which one it is if you're given the formula? Okay. And recall that I said in the beginning, a general equation, that the number of cations plus the number of anions equals the charge of the, the charge of the compound. Okay. All right. So let's go back to that simple equation again and take a look at this example here. All right. Well, we don't know what zinc is charged, so we can say zinc is charged plus the chloride. Okay, well, we know what the chloride is, right? Because chlorine is in group 7. And when it becomes an ion, it becomes chloride with a -1. And there's 2 of them. Okay, and so there are 2 -1 charges coming from the chloride. So I can do this, right? Equals 0. Isn't that correct? Because together, I put copper. Why did I put zinc? Sorry, I had zinc in my head. Cu plus the charge of the anion, which each one is a -1, and there's 2 of them, so I get a total of -2 equals 0. And so now I have a real simple algebraic equation where I'm solving for copper. And so I got to move the -2 over to the right side. And guess what happens? That means that copper is equal to a +2 charge. And that is consistent with the formula I'm given. That must be a +2 because there's 2 chlorides, each one with a -1. So that implies that the name is copper, Roman numeral 2 chloride. Okay. You see how we work that through? We set up a general formula, the copper, because we don't know what the charge is, because we recognize that copper is a variable oxidation number, and we haven't been given which one it is. But what we do know is this, that the anion, we know the charge of the anion. The chlorides are each -1, and there's 2 of them. So the chlorides bring in a -2 total charge. So I can say copper plus a -2 equals 0, because the overall charge of the formula I'm given is 0. I can just solve for copper. Solve for copper means that copper must be a +2. Okay, +2 and the -2 equals 0. And therefore, I'm using the copper 2 ion here. All right, that's the copper 2 ion, and that's the name. All right, so let's do this. Here we have the similar scenario. We got lead, which is not part of the 16. Okay, so we can set that up as the real general formula. Plus, okay, we have 2 oxygens. In ionic form, each oxygen has a -2 oxidation state, and there are 2 of them. So that gives me a total of -4, does it not? Yeah. Okay. That means there's a total of -4 for both oxygens. What does that infer? That lead must be a +4. And so its oxidation state is a Roman numeral 4. Oh. Okay. Those Roman numerals are in capital letters, by the way. All right. Excuse me. So the name we have here is lead, Roman numeral 4 oxide. Okay, let me do a couple, let's finish with this page and we'll call it a day. All right, so we got nickel. Nickel, we don't know its oxidation number. It's one of the variable ones, okay? So what do we know about the bromide? The bromides are -1. Why? They're bromines in group 7, each, and it becomes bromide, becomes a -1. There's 3 of them. What does that infer that nickel must be? That must be nickel 3. Sure enough, that is nickel 3 bromide. Okay. Oh, manganese, sorry. SO4. SO4, you might think sulfide, right? Okay, here we go again. We got sulfur, and you might think sulfide, but we look immediately to the right and you've got oxygen. So that means polyatomic ion. Go to the polyatomic ion, it's going to be either 4 or 3 using SO4. That is called the sulfate. The sulfate has a -2 charge on the polyatomic ion. Okay. What does that tell you about the manganese? It's got to be a +2 because a sulfate is a -2. That means that you are using manganese Roman numeral 2 sulfate. Okay. Copper, similar. We got a polyatomic ion here. We got nitrogen. I'm going to continue with the scenario. I'm repeating myself. It may sound redundant, but there's a reason behind it. Okay. Setting up a systematic approach at the problem. You got nitrogen. You're thinking nitrite. You look over to the immediate right. There's an oxygen. No longer think nitrite. Think nitrate or nitrite. Which one? You go to the polyatomic ion table. You see there's NO3, which is nitrate, and it has a -1 charge. Okay, that means that copper, this copper must be a +1. Therefore, Roman numeral 1, copper, Roman numeral 1, nitrate. And then finally, you got cobalt, CO. Now, carbon monoxide, remember, has cobalt. Second letter is lowercase. Now you see nitrogen, okay? You think nitrate, you double check, nothing to the right of that nitrogen, right? That means it's nitride all by its little self. Okay, there's no nitrate, no nitrite involved here, simply because there's no oxygen immediately to the right. Go to periodic table, it's in group 5. We know that nitrogen becomes nitride with a +3 charge. That infers that cobalt must be a +3. And therefore, the name here is cobalt 3, Roman number 3, and nitride. Okay. Finally, a little more challenging, but that's okay. Okay. Let's do this. Last one, and then we'll call it. I'm going to go over it a little bit. CO3, it's in parentheses. Okay. It's in parentheses, should flag you to go to the polyatomic ion. Okay. Go to the polyatomic ion, CO3, which is down here, has a -2 charge. That is the carbonate, -2 charge. And there's 3 of them, right? In the parentheses outside, there's 3 of them. And so what do I do in my algebraic equation? Well, I'll set this up. I don't know what, there's 2 irons, is there not? There's 2 irons because there's a subscript 2 there. So I can do 2 FEs, 2 of them. Okay. Now I just found out that the CO3 carbonate has a -2 charge, and there's 3 of them there. So that's a total of -6, is it not? That's my general algebraic equation. Okay. Now, if I solve for FE here, I got to move the -3 over to the right, which gives me 2F equals +6, right? And if I take F and I divide through by 2, FE is equal to +3. And so that tells me that those ions each one is an iron 3. I got 2 of them for a total of a +6 charge. I just calculated that each carbonate brings a -2, and there's 3. There's a -6. Remember the common number we dealt with earlier? So the common number here is 6. I got 6 negatives and 6 positives. Okay. And in order to get 6 positives, I only have 2 irons, and each one must be +3. So therefore, I'm using iron 3 carbonate. Okay, so give that one some thought and work that one through. It's probably the most challenging one right there. But work through the algebraic equation I just gave you to figure out which one did I use here. All right, well, let's stop it here. Sorry, I took a little bit extra.